Hi everyone. We're continuing with continuous uniform distributions. In particular, this basic distribution, the continuous uniform distribution on this interval from 0 to 1. All right. Now again, remember that we relate areas with probabilities. That's a key theme of this lesson and in fact for much of this class. So let's say that X has as its distribution this distribution, a continuous uniform distribution on this interval from 0 to 1. So X can take on any real value between 0 and 1. Okay, then let's find the probability that X can be some value between 0.2 and 0.7. All right, turns out to be 0.5. Now, why is that? Well, we look at the corresponding area. So from 0.2 to 0.7, what is the width from 0.2 to 0.7? Well, 0.7 minus 0.2 is 0.5. So 0.5 is the width, 1 is the height. Area of a rectangle, like this gray shaded rectangle, is base times height. 0.5 times 1 is 0.5. That's the area of this gray shaded rectangle. Therefore, that's the probability that we're looking for. The probability that X is between 0.2 and 0.7, if it's generated like so, that probability is 0.5. So in other words, this gray shaded rectangle makes up 1/2 of this square. Again, areas correspond to probabilities. The shaded region is a rectangle with base 0.5 or width 0.5 and height 1. I know it's a little confusing because before, widths or bases would be 1 and then the height would be the probability. Here, it's kind of flip-flopped. Here, the width basically gives us the probability and the height is 1. Okay, now you might be asking, what happens if instead of is less than, we have is less than or equal to, but it turns out not to matter. So the probability here for all three of these probabilities have the same probability as before. It's going to be 0.5 for all of these, because it doesn't matter whether you include the actual line segment here or not. It doesn't matter if you include the actual line segment here or not. The area here is still 0.5, regardless of the actual boundaries, whether or not they're included or not. And that's because the probability that X is exactly 0.2 is 0. The area of this line segment is 0. Likewise, the probability that X is exactly 0.7 is also 0. The area of this line segment over to the right is 0. So for continuous distributions, again, it does not matter. It does not matter whether you have is less than or is less than or equal to. So as far as these kinds of probabilities go, it doesn't matter whether you have bars underneath here or not. It does matter that this number, the 0.7, is bigger than this number over here, the 0.2. If these were flip-flopped, or if you were to reverse the symbols, then the answer would be 0. Okay. Now in general, if instead of 0.2 to 0.7, what if we have some other interval? Let's say this interval from x1 to x2. Probabilities for continuous uniform 0-1 distributions. Assume that X has as its distribution this distribution, uniform 0-1. So the probability density curve is just this flat line segment up here with height 1. Okay, now we have a total area of 1 inside this square, this 1 by 1 square, all right? But let's say that we want to know the probability that X falls between x sub 1 and x sub 2. Well, again, the area of a rectangle is given by base times height. The height is 1, which means that the area is given by just the width, or the base here, which is x sub 2 minus x sub 1, the width of this subinterval over here. So the probability that this random variable is between x sub 1 and x sub 2, I'm assuming that x1 is no more than x2, this probability is going to be the larger value minus the smaller value. And of course, both these values have to be between 0 and 1. The probability you get something between 30 and 50, say, is going to be 0. There's nothing out here, really. Okay, so the probability that x takes on a value between, for example, 0.2 to 0.7, that's going to be 0.7 minus 0.2, or 0.5. Okay, so now let's say that instead of the interval from 0 to 1, our continuous uniform distribution goes from 30 to 50, or from 2,000 to 3,000, in general, from A to B, assuming that A is less than B. So how do we deal with these continuous uniform distributions on a more general interval? Maybe not from 0 to 1, but from A to B, where A and B are real numbers and A is less than B. Okay, so X has as its distribution a uniform distribution, a continuous uniform distribution on A to B, meaning X can be any value between A and B. All right, well, let's take a look at this picture. Now remember that total probability is 1. The total area of the rectangle here has to be 1. Now, if we're looking at possible values of x being between A and B uniformly, then the width or base of this rectangle is given by B minus A. That's the width or base of this rectangle. The height of this rectangle is given by 1 over B minus A, the reciprocal. The reason being that we need this times this over here. I need, once again, this times this over here, that product to equal 1. So the height of this flat top, the density function, must be given by this value over here, the reciprocal of the width. Okay. Now let's say that we want to know the probability that x will be between the values x sub 1 and x sub 2, where again, these two values are between A and B, and x sub 1 is, let's say, less than x sub 2. Then the probability that x, which has this distribution, continuous uniform from A to B, the probability that x is between x sub 1 and x sub 2 is given by this fraction over here. And there are two ways of looking at that. One way is to look at it in terms of areas. So the area of a rectangle is given by base times height. The base, or the width, is given by the width of this subinterval, x sub 2 minus x sub 1. That's the width or base of this gray rectangle. The width of this subinterval is x sub 2 minus x sub 1. The height is given by 1 over b minus a, the reciprocal of the total width of this rectangle. Well, base times height. Base is x sub 2 minus x sub 1. That's this over here. The height is 1 over b minus a. The area of a rectangle is base times height. Base times height. This fraction, x sub 2 minus x sub 1 over, I'll use a different color now, b minus a. So basically, it's the width of this subinterval for this gray rectangle over the total width from A to B. And in fact, that's a second easier way of looking at it. Look at this fraction over here. What is the area of this rectangle? What proportion of 1 is the area of this gray rectangle? Well, since we have a common height all the way throughout, the proportion that this gray rectangle makes of the total rectangle over here is going to be the proportion of this red subinterval to this purple total interval. So for example, if this red subinterval, the base of this rectangle, is 1/2 of the total interval from A to B, then the area here, the gray area, is 1/2 of the total area. And the probability that x is between these two numbers is 1/2. So again, a simpler way of looking at this is that the probability that a uniform AB random variable lies between x1 and x2, it's equal to the proportion, the ratio of this smaller width to this larger width. It's a proportion. So if this width is half of the total width, the probability is 1/2. If it's a third, the probability is a third, and so forth. Now, in our next example, we're going to actively apply this formula. On a test, this formula will be given. So let's say that we have a continuous uniform distribution on this interval from 2 to 10. So A is 2 and B is 10. These are the endpoints of our larger interval. 2 here and 10 here. First of all, I'd like to go to Excel and show you how we can generate some random variables with this distribution. And actually, Excel does require on a formula technique. Now, first of all, you may remember from the last lesson that to get a random number between 0 and 1, this is for a uniform distribution, 0, 1, where x takes on a value from this distribution, we would put equals rand and then a pair of parentheses. In fact, we can take 3 random generates from this distribution, and here we have 3 random numbers between 0 and 1, this continuous uniform distribution. So for example, lower numbers in the interval are no more likely than higher numbers, or vice versa. Now, what if instead of a uniform distribution between 0 and 1, let's say we wanted a uniform distribution between 0 and 8. So we get random numbers between 0 and 8. Or again, we have a flat top. It's a continuous uniform distribution. The width of this interval is 8. So what we do is we would use equals rand, parentheses. So this would give us a continuous uniform 0, 1 random variable, a value for that. But then if we wanted something from a 0, 8 interval, we would take this and multiply it by 8. So here, this number here would be a random value from a uniform 0, 8 distribution. It's about 6.2. We can take 3 of these. So here we have 3 random values from this uniform 0, 8 distribution. Again, there's no favorability towards lower values, higher values, or middle values. But wait a minute. What if we want random numbers between 2 and 10? So basically, we want to lift up this distribution by 2 units. We want random variables from a uniform 2, 10 distribution. Well, we take 0, 1 random variates, those values, multiply by 8 so that the width is 8. But since the bottom number is 2, since A is 2, we add 2. So we basically lift up all these values by 2 units. And here we get a value between between 2 and 10. We can do 3 of these, let's say. Again, here we have 3 random values from this distribution, a continuous uniform distribution from 2 to 10. It required some hacking in Excel. There's not a super clean formula for this, but you basically exploit the basic rand function that we used before for the classic continuous uniform 0, 1 distribution. So if your scientific calculator or Excel or your program can produce these kinds of generates, if it can work with this basic distribution, then you should be able to manipulate this to get continuous uniform generates from more general continuous uniform distributions, whatever A and B are. Again, you multiply by the width to get these, and you add by A, the minimum value, to get these. Okay. Anyway, that's the distribution we've been talking about, a continuous uniform distribution from 2 to 10. But let's say we want to know the probability that a random variable from this distribution will take on a value between 4 and 7. Basically, what's the probability that this value was going to be between 4 and 7? Okay, we can use this formula where x sub 1 is 4. That's the minimum value that we're interested in. X sub 2 is 7. That's the maximum value that we're interested in. All right. A is 2, B is 10. That was fixed in the distribution. So we want to know what proportion does 4 to 7 make out of 2 to 10? Well, x sub 2 minus x sub 1, 7 minus 4 is 3. That's the width of this gray box over here. over, well, what's the width of the bigger box over here? It's b minus a. 10 minus 2, or 8. 10 minus 2 is 8. So the probability that x is going to fall between 4 and 7 is going to be 3/8 or 0.375. That's the proportion of area that this gray shaded box makes out of this big box over here. But because we have a flat top, we can just look at the numbers down here. 4 to 7, that's a width of 3 units. 2 to 10, that's a width of 8 units. 3 out of 8, that's the proportion, 3 out of 8. So the probability that x, which is from this distribution, the probability that x is between 4 and 7 is 3 out of 8. All right, so that takes care of continuous uniform distributions. Next, we're going to go back to our favorite shapes, these bell curves, next time.